In this video, we're going to discuss what is a PN junction diode and what is the application of a diode in a network. A PN junction diode is basically a device which allows unidirectional flow of current. That means this PN junction diode that you can see here will only allow current from P side to N side of the diode. So from P side to N side, what actually happens inside the diode so that it allows current, but in the opposite direction it does not. Here I am holding a common diode that is often sold in the market. It goes by the name 1N4007. It is from a 1N400X series, and this is the latest diode. That means this has a peak inverse voltage of 1000 volts. So in this diode that you can see here, the P side is the black one and the N side is the slight grayish one that you can see here. It is a slight grayish one. This side is the cathode and this side is the anode. So the orientation of the diode will be like this. So when I am applying voltage from P side to N side, the diode actually allows the current to flow, but in the opposite direction it does not. So this is a cross section of a PN junction diode, in which we can see that there are two types of substrate here. That is the P type and the N type. The P type substrate of the silicon is generally doped by a acceptor atom, and the N side of the silicon substrate is doped by a donor atom. This side, on the P side, we generally have aluminium as the dopant, and on the N side we have generally phosphorus as the dopant. Phosphorus has 5 electrons in its outermost shell, but aluminium has only 3 electrons in its outermost shell. So in order to fill the octet, this phosphorus atom has to release an electron, and this aluminium atom has to accept an electron. So aluminium becomes an acceptor and phosphorus becomes a donor. When the silicon substrate is doped with aluminium atoms, what happens is aluminium accepts the electrons that are intrinsically present in the semiconductor. So when it accepts the electron, it becomes a negatively charged ion that I have shown here with the negative charged and one circle here. This is the aluminium ion that has accepted an electron in its outermost shell. So this aluminium now has 4 electrons in its outermost shell and it has completed its octet. But there is also a formation of hole in this substrate here, because the aluminium has to attract an electron from somewhere. So it will attract an electron from the silicon-silicon covalent bond. So it will break the bond and attract the electron into its orbital. When the silicon substrate is doped with phosphorus, it becomes N-type substrate. Why? Because phosphorus has 5 electrons in its outermost shell, and it will release 1 electron in order to complete its octet. So when it releases an electron, it actually becomes a positively charged ion. So I have denoted this phosphorus ion as positive encircled, and this negative charges that you can see here is the electron released by a neutral phosphorus atom. When it releases electron, it becomes a positively charged ion, and the electron floats around the substrate, that is the N-type substrate. Now in equilibrium, what happens is when you join these two substrate here, actually we don't join, but let us assume for the sake of simplicity that we join these two substrate here. What actually happens is that electron drifts into the P substrate and holes drift into the N substrate. So because of that, the electrons and the holes recombine within each other, but the ions do not actually react. So electron and holes when combined becomes neutral, but the ion remains charged, and because of that, in the depletion region that we can see here, I have shown the depletion region by dotted lines. So this is the depletion region that you can see. In the depletion region, what happens is that it gets devoid of any type of charge carriers, either holes or electrons. So the depletion region is not allowing any sort of transfer between the substrates. Neither it is allowing the hole transfer and neither it is allowing the electron to move from the N side to P side. And depletion region that you can see here is actually formed because of the barrier between two charges. So in the left side we have the negative charged, that is the aluminium ion that has accepted an electron, and on the right side we can see that this is a phosphorus ion present in the depletion region. And because of these charge differences, there will be a built-in potential within the PN junction. This built-in potential is often called as phi Bi, or the cut-in voltage. Because of this depletion region, what happens is that there is an electric field from the N side to P side. Because of this electric field, the holes get repelled to the left side and the electrons get repelled to the right side, so they are not allowed to combine anymore. Now if we want to make this PN junction conducting, what we have to do is to just make the forward bias voltage. That means we have to apply a higher voltage on this side and lower voltage on this side, and the diode will get forward biased. We have to make the forward bias voltage more than the cutting voltage. Now we can see that this diode is connected with a resistor, so there will be no problem in flowing of the current. But the current in a PN junction diode is not a linear relationship with the forward bias voltage. Instead, it is an exponential relationship. So let's see what is the relationship between the current through the diode and the voltage applied across it. So this is the general characteristic of a PN junction diode, in which we can see that on the positive x-axis I have shown here the forward bias voltage, on the negative x-axis I have shown the reverse bias voltage. That means we are applying positive voltage on the N side and negative voltage on the P side, then the diode will become reverse biased. And I on this side is in the positive y-axis we have shown the I current moving from P side to N side. In the negative y-axis we have shown the current moving from N side to P side. So let us understand, when does the diode actually conduct? As I have said in the cross-section area of the diode, that when we apply a voltage more than the cutting voltage in the forward bias mode, the diode actually starts conducting. So what is the cutting voltage here? For a general silicon based diode, for the diode that I have shown in the beginning, so this is the diode I was talking about. This is the 1N4007 diode. This has a cut-in voltage of typically 0.7 volts. This is a silicon based diode. Silicon based diodes generally have a cut-in voltage of 0.7 volts, whereas germanium based diode have a cut-in voltage of 0.3 volts. So we can see that it does not require a lot of voltage to make the diode forward bias. But in the reverse bias voltage, what actually happens is very interesting. When we apply a reverse bias voltage, doesn't matter it is smaller than VBR or larger than VBR. I will explain what VBR is. So when it is smaller than VBR, even though it is smaller, PN junction diode actually allows some amount of current in the reverse bias, and that is called the reverse saturation current. The reverse saturation current is actually due to the minority carriers, not the carriers that I have explained in the cross-sectional area of the PN junction diode. Actually, on the P side also we have some amount of electron. Those are called minority carriers. So because of those minority carriers, this reverse saturation current arises. This reverse saturation current is actually a dependent of temperature. It does not depend on how much voltage we are applying on the reverse bias. So if we want to increase it, that means we want to bring it down, make it more negative, we want to bring the IS here, we have to actually increase the temperature. If we increase the temperature, then the flow of minority carriers from N side to P side will actually increase. What actually happens in the diode if we cross a certain amount of voltage in the reverse bias? That is called the breakdown voltage. For the diode that I have shown, 1N4007, that has a reverse breakdown voltage of 1 kilovolt, that is 1000 volts. So when I apply more than that voltage, what actually happens is that the current starts to increase violently. That means there is a breakdown in the diode. This is called the avalanche breakdown. So this happens also because of the minority carriers. A very large amount of minority carriers starts moving from N side to P side. So let's understand the value of forward bias current and reverse bias current in a PN junction diode. Actually, in a PN junction diode, the forward bias current has a different equation and the reverse bias current has a different equation. So the equation in the forward bias mode will be, so this is the equation of the current in forward bias mode. So here we can see that this is the reverse saturation current, this is the forward applied voltage, this is the ideality factor of the diode, this is the threshold, and this is the thermal voltage at the particular temperature. Usually the thermal voltage is 25 to 26 millivolts. The ideality factor is 2 for silicon and 1 for germanium. In the reverse bias mode, the diode will have the different equation. That current equation will be, so here also the IS is the reverse saturation current minus VR. The minus denotes the polarity of the voltage, that we are applying more voltage in the N side now. So VR is the reverse saturation, reverse voltage, and eta is the ideality factor, and Vt is the thermal voltage. So for the demonstration of working of the diode, I am going to make a simple circuit consisting of one LED, one PN junction diode that I have shown, one kilo ohm resistor, and a power supply. So this is the circuit that I am going to make. This resistor is 1 kilo ohm. So this is the LED that I'll be using. This is the anode of the LED and this is the cathode of the LED. Similarly, this is the anode of the PN junction diode and this is the cathode of the PN junction diode. Once I am going to make the PN junction diode forward biased, and I am going to connect it in the reverse bias mode also, so that you can see that it actually allows the flow of current in the reverse bias or not. So this is the simple circuit that I have made. The red one is the positive terminal of the power supply, the black one is the negative terminal of the power supply, the 12-volt power supply that I have taken. So this positive, the anode of the power supply is connected to the anode of the diode. That you can see, the diode is connected. This side of the diode is anode, this side is the cathode. That you can see, this is the gray portion of the diode. That means this is the cathode and this is the anode of the LED. So the cathode of the diode is actually connected to the anode of the LED. That means both the PN junction diode, LED is also a PN junction diode, so both of them are forward biased. The LED is connected via 1 kilo ohm resistance, then the 1 kilo ohm resistance is connected to the negative terminal of the battery. So this is the complete circuit. Now I am going to power it on. So you can see that the LED is glowing because the diode is forward biased. Now what I am going to do is I am going to connect it in the reverse bias mode. So this is the diode that I have taken here. This side is the anode and this side is the cathode. Now what I am going to do, I am going to reverse it. That means the cathode side is going to be connected to the anode of the power supply. So the circuit is now again complete, but the diode is in reverse bias. This is the cathode of the diode, this is the anode of the diode. The cathode of the diode is connected to the anode of the power supply, and the anode of the diode is connected to the cathode of the power supply. Now I am going to turn on the power supply and see whether the LED glows or not. So you can see that nothing actually happened. That means the diode is in reverse bias and it is in non-conducting mode. So that's all for today. See you in the next video.